Hi and good afternoon, everybody. Many thanks for joining us today. Today we are talking about masonry construction design and more specifically how MasterSeries 2025 is transforming the way we approach it. Over the next hour, we will explore the brand new Masonry Design Module and show you how it takes masonry design far beyond the traditional sub-panel method. My name is András Förbély. I'm the sales manager here at the MasterSeries, and today I'm joined by my colleague Martin Ogara, our director, who is the key person behind the development of our masonry design solution. Martin will start with a quick overview of the background and the engineering challenges behind the traditional masonry design, and after that I will take you through a live demonstration of the new masonry design module, highlighting the latest functionality and workflow improvements. Before we dive in, just a quick bit of practical information about using GoToWebinar. The control panel can be hidden using the red arrow button at the top. If you would like to send us a question or message, please use the chat option on your panel. Feel free to type your questions at any time during the session. We will answer some as we go, and we will also have a short Q&A session at the end. As usual, this webinar is being recorded. The recording will be posted on our MasterSeries channels and also sent directly to your email address, so you can rewatch or share it with colleagues later. Here is a quick look at what we will cover today. So first, Martin will take you through the background, the challenges of the traditional sub-panel method and why it falls short. Then we will look at how MasterSeries 2025 changes the game, enabling full wall masonry design, including complex geometries and multi-story walls as a single unit. After that, I will lead a live demonstration to show you how the new workflow, advanced yield line analysis, and internal lateral support features work in practice. And finally, we will wrap up with a Q&A session at the end. So let's get started. I am handing control over to Martin.
Well, good afternoon, everyone. Just to extend András's welcome to you to this webinar. Hopefully you can all hear me and you can also see my PowerPoint screen.
Yes,
so we're just going to take you through a very, very brief summary of the age-old problem of lateral load design in masonry and how the codes approach it, and the problems that the traditional methods bring, or the limitations that the traditional methods bring, and how MasterSeries attempts to solve those. And as we've been solving this problem for quite some time, and what we're talking about today is really the background and what we've done to date, and then what MasterSeries 2025 brings to the table in terms of extending those existing solutions. I thought it'd be useful to start off with just a little bit of an indication of some very useful publications, 3 very, very useful and publications for a high-level summary of the Eurocode 6 were introduced back when Eurocode 6 2005 was introduced by the Concrete Centre, and these provide a very, very good and pragmatic overview of the main sections of the code, and they're, I think, an excellent resource for anyone wanting to just to get a little bit of an introduction to this area. And in addition to that, well, obviously, in addition to the actual code of practice itself, we find that the BSI published document 6697 and the later version of it, the 2019, is indeed a very useful publication for giving engineers practical advice in relation to masonry and when you can assume something is a restraint or not a restraint based on the actual construction situation. So there's some really useful and practical advice there on that, and in this area, which is probably the main thing that designers struggle with in terms of understanding what options you need to choose in the software that reflect your real world situation. Onto the topic then, specifically we're talking about lateral load, out of plane lateral load design and the use of yield line analysis. Now, whether you know it or not, the approaches that the design codes take, both British Standard 5628 Part 1 2005 and the later Eurocodes, in addition to Eurocode 6 and Eurocode 6 2002, the very latest version, they all give us a method by which to design for lateral load based on bending moment coefficients. And these bending moment coefficients are actually derived from yield line analysis. And from that third publication from the Concrete Centre, just showing there a little bit of a indication of the types of things this is replicated from the codes, and the coefficients that you get between the various codes are identical because obviously the underlying theory of the yield line that the coefficients are based on does not change. So these are entirely replicated across the different codes. And they basically give a number of different patterns of wall support conditions, and using the ratio, the orthogonal ratio of the flexural strengths in the perpendicular and horizontal direction, the perpendicular and horizontal direction, we develop a mu factor, which is the ratio of those, and then with the wall aspect ratio, we can basically pick out from the appropriate table the bending moment coefficient. And that's indeed what MasterSeries traditionally has been doing. If you're a more limited power pad user of MasterSeries and you're designing walls for lateral load design, that's indeed what you're doing. It's also what's happening when you turn off the advanced yield line analysis, which we'll come to. But this is this bending moment alpha coefficient that that's been derived, which helps us arrive at an actual applied moment value, all based on plastic yield line theory. Maybe some people hadn't appreciated that's what that was actually based on, but that's we've been doing yield line analysis effectively in masonry design from for many years. And then furthermore from that, then all of these obviously are replicated in the various annexes and places of the code, but both codes, both the British code and the Eurocode and the latest version of the Eurocode, permit the use of more sophisticated analysis techniques for walls that are more complex than the simple shapes without openings. So obviously that complexity arises when we have got one or more openings. We might have other things going on like wind posts, or and then we're into now more irregular shaped walls, walls that aren't rectilinear in MasterSeries 2025. So the use of more sophisticated analysis techniques is very much permitted. One of the things that's often pondered is obviously a yield line analysis method is a plastic analysis method, and obviously we're well familiar with it being traditionally being used for reinforced concrete slabs, because obviously it's you're able to go plastic with your reinforcement and redistribute some moment. But in a brittle material like masonry, it does raise an eyebrow when we talk about doing a yield line analysis for masonry. And we've been satisfied that the background of the code and the permission of the using of yield line analysis is solid, because it is based on tests and it is based on the behavior of particularly the yield lines that form in a diagonal fashion, and how they are typically going in a stepped fashion through the mortar beds and perpend joints, and how that inherently actually gives us an amount of rigidity and an amount of rotational capacity beyond the tension capacity of the masonry itself. So a lot of the permission to use yield line analysis is based on solid evidence from tests and from numerical modeling. So just to put that out there. So moving on to then the more typical problem of not having the luxury of having walls that don't have any complexities or openings. They always do. In the British standard, it was the first standard really to talk about how we might deal with this here, and it presented a simplified solution for taking the wall and splitting it up into sub-panels, and then dealing with each of the 4 panels that we see here in a similar fashion that we would deal with an individual panel, using those tables and the codes to derive bending moment coefficients. So taking that, then this would be split up into 4 panels with a free edge on these edges, but then the loading from the panels above and below and the load from the opening itself would have been transferred as a lateral edge load to those panels. So you've got a 2-way spanning panel with a free edge, and then we would do the design on those. And noting here, you know, unity ratios of about 0.339, 0.34, with something quite small, I think it was in those ones, but those were the key ones here on that. The code, when we look at Annex E of BS 5628, you would also see the possibility, it was entirely the engineer's choice whether you could actually choose to split up the wall into horizontal subpanels or into vertical subpanels. There's no guidance given on that. It was very much an intuitive thing that the engineer might choose based on what they felt was a more appropriate way to split up those panels for their given situation. How would they expect the panels to more suitably behave? I would argue in this situation the vertical spanning route was more appropriate, but this does highlight one of the first major limitations with this sub-panel design methodology, combined with the moment coefficients that are presented by the code. And what we can see here is this top sub-panel is now giving us a unity ratio which is failing, which is very, very different from if we just go back to what we had here. So how can these 2 positions for the same wall be so different? Which is obviously one of the questions that designers often ask, and we often got asked whenever we were using these types of techniques. What's actually driving this here situation is the limitation in the codes of the tables presenting bending moment coefficients for specific H over L values. Height here being 3, the length being 5, so we have a H over L ratio here. But with regards to the sub-panel, it is only 1 meter high and 5 meters long, so it actually has a H over L ratio of 0.2, outside the scope of the 0.3, which then forces us to take the decision that we cannot, in accordance with the bending moment coefficient tables, use values there. So we've got to then assume that this is one-way spanning. Of course, one-way spanning can't happen vertically, because in the sub-panel methodology, this would be taken as a free edge, just like it was in, except for the horizontal orientation here. So it has to span horizontally, effectively ignoring this lateral restraint on the top edge, which is why we're getting such a large unity ratio here. And this has been demonstrated to be, you know, a very conservative approach, and one that we were bound to with regard to the restrictions that were presented with the sub-panel methodology and the bending moment coefficients of the code. One more method actually worth noting that we did have, well, I suppose just to say that our implementation of the sub-panel methodology did allow up to 2 openings. So the sub-panel, whilst the Annex E in 5628 only showed 1 opening, there was no reason why that same methodology couldn't be extended to 2 openings, and we weren't comfortable going any more than that at that time with 2 openings. I suppose you could quite easily argue that if we had a longer wall with another opening, why not just keep doing more and more sub-panels? But that's the limitations that were presented at the time. So we could do 2 openings. Now, one more method that was available to designers was something called the reduced fixity small opening method. And this method effectively, I think it's a very elegant solution to a complex problem, because it does have its limitations in that the opening can't be too large, and it also must be centrally placed, because effectively what it's doing in a roundabout way is with this, this was previously 100% fixed, and then we have a length of opening here which is 1 meter over 5 meters, so that's you know, something that's 20%, and now we're seeing a reduction, and this is 1 meter over 3 meters, so we're seeing a reduction in the effective restraint on these conditions at these edges, so that the reduction of the fixity has the same effect of reducing the yield line capacity, which is exactly the same as reducing the length of the yield line. So in a roundabout way and in a convenient way, it actually was eliminating the yield lines that would have occurred through the opening, whilst still assuming that the original assumed yield line pattern had occurred. Now this may be obviously meeting in the middle and performing more of an envelope type of pattern, but the same principles applied. We were eliminating the lines that would have occurred in the opening region. So you can see how that method is nice, but it does certainly have its restrictions. So moving forward a little bit, and again, we're still talking about history here. We're not talking about anything new. We first introduced automated yield line analysis in MasterSeries 2016, so that long ago. And if we can remember back to that first panel that we looked at using the bending moment coefficients, the nice simple plain panel with no openings, we were getting a unity ratio there of 0.95. So that's almost entirely replicated here now with this now advanced automated yield line analysis, which is obviously reassuring for designers. 0.7% less than the actual solution, but we're not going to argue about that. It does yield potentially, patterns that obviously taking into account the orthogonal ratio of the masonry, you can end up with patterns which are slightly different than what the original assumed pattern would have been, whereby you just simply had the classic envelope shaped yield line pattern appearing there. So the advanced yield line analysis obviously has the opportunity to look for other patterns, and it's maybe found something that's ever so slightly less than the alternative pattern with forming yield lines at these corners, because we've got a fixity along the bottom. So there's a very, very minimal difference between obviously the optimum yield line and then what engineers would assume to be the best fit for simplicity. So I don't think designers should be too worried about that. This is a numerical method, is obviously important to say. Without going into any boring detail, it simply is a numerical method that using some linear programming solving and a presented mesh of elements, which we do some adaptive meshing on, and but effectively using geometric techniques, we're using linear programming to solve the mesh and adapt the mesh to a situation whereby we're presenting and finding the most critical or minimum energy yield line pattern for a vast number of possibilities. When you click that analyze button in the masonry program, that's what's happening in the background. There's a lot of heavy lifting going on to arrive at even just this situation here. So obviously where this method wins is not really giving us any advantage in this particular situation, is where you've got your openings. So even with your two openings, you can see here now that obviously you're getting a nice simple yield line pattern, which is giving us a unity ratio there, a single unity ratio for the whole panel, nothing divided into sub-panels, and it's all in accordance and in line with the permissions of the code. Obviously, beyond what we were able to do with regards to two openings, we can now go to three openings. Again, getting some interesting patterns here. We do have an option in the software to investigate the effect of mesh density. So there is options where you can say, like, use a coarse mesh density or a superfine mesh density, and that's generally only something that you need to tinker with if your numbers are getting close to unity. And we would warn you about that in the software. We would maybe say that your mesh densities, if you're up at 0.95, we would maybe say to you, if you're using a coarse mesh, you might want to use a refined mesh, and there's options in the software to do that. The obviously disadvantage of using a more refined mesh is it does bump up the analysis times, and it makes the software less instantaneous to work with, in terms of it's not possible to do what we would have traditionally done, in that everything's updated instantaneously with every single change that you make. You tend to turn off the auto solve in those sorts of situations, and then just only solve it when you have to, which is absolutely fine. The other things that it does, that the advanced yield line analysis gives us, is the ability to consider things like wind posts, and far from the wind post just being a line of support, we actually model this with its plastic capacity, and where the overall panel might yield through the post, the software will tell you that. So if there's a minimum energy situation where the whole panel is going to yield along with the post, you will see that, and that's probably something you want to avoid. You want to put the post in so that it does actually yield either side of the post. This is analyzed as one domain, but it's found that the minimum energy yield line pattern has occurred on this side of the post, and it effectively means that if there were another yield line pattern to occur here, it would be guaranteed to be less than the 0.267. So as one domain, this is the most critical pattern, which is all we really need to know. Okay. The other thing about our advanced yield line analysis that many people don't appreciate is that when you're dealing with walls that are stiffened with piers and it's two-way spanning, those piers aren't taken into account in terms of the lateral and enhancing effect. Piers, vertical piers, stiffening piers are only beneficial for non-advanced yield line analysis for the traditional methods of lateral load design. Whenever you're purely vertically spanning, it's not possible really to use those methods to accommodate the effects of piers in a two-way spanning panel, but it is with the yield line analysis. With the yield line analysis, we do model different zones with the increased plastic capacity, and that allows the more sophisticated analysis to get you a better outcome with your piers, even in a two-way spanning panel. So those are the things that we've been doing for quite some time. You guys have been taking great advantage of it. We've enjoyed seeing the things that people have been doing with MasterSeries over the past 9 years. And we've been listening to your feedback, and it's taken us some time, but we're pleased to say then, based on what you guys want, what our customers want, we've been able to extend the masonry program to beyond rectilinear panels. And the big thing that you're always asking for was obviously driven by domestic situations, was dealing with gable wall shapes, and we were handling gable wall shapes that are both symmetric and asymmetric, and also hipped roof situations as well. And whenever we started thinking about, the step from a rectilinear panel to a gable wall panel in terms of the out of plane analysis actually wasn't terribly difficult. It involved us doing some parameter testing on how we develop a mesh and present a mesh and adapt a mesh, and that work, as I say, wasn't technologically a huge step for us to make. But when we did do this, we thought, well, there's actually probably limited value in looking at this at a whole wall if we have an intermediate lateral support at ceiling level, which would probably be the case. Again, this is where PD 6697 is very useful in saying to you, okay, well, this is a situation where you can take that timber roof as laterally restrained. It'll tell you you've got joists spanning this way. You've got to, stiffen them with braces or noggins or whatever you call them in the perpendicular direction. And how you tie it to the wall. It'll tell you all these things for when you can take that lateral restraint into account. So we'd recommend you look at that. But by and large, we say yes, okay, well, people are going to want to do that in this situation. So that's where we introduced the intermediate internal lateral restraints. I have drawn over the top of this here with a thick black line just to accentuate where these intermediate lateral restraints are. They can be across the full panel, they can be horizontal or vertical. We haven't done any vertical ones in this arrangement, but the same input can be used for both. They do need to be tied back to the main boundary. They can't be floating in the middle of the panel. That's the only geometric restriction we have on them. But they can be partial, as we have here. And this actually then does create two domains in the wall in terms of yield line analysis. So this is a completely separate yield line analysis to this whole domain here. With its restraint coming in part way. If this were all the way across, then we would have three domains of yield line analysis. Probably the bigger part of the work in terms of what MasterSeries 2025 brings in terms of those things is the ability. What snuck up on us is basically that we're now dealing with not just a single panel, but multiple panels and multiple levels. Even in this single domain analysis for yield line, when we're doing our vertical load check now in this section of the wall, we obviously have two levels. So we'll be doing a buckling check between this level and this level. So that is reflected in when we look at our vertical load takedown, and Andres will show you how to turn this on and off. You can see the sample locations of where the buckling check forces are being taken at, and that gives you a good indication as to where the checks are being performed and where indeed the buckling check is going to be performed at. So we can see here, yes, we've got our gable zone. We've also got this zone in here, which will be in terms of a level on the force at the 0.5 H of that level. And again, down in this zone, where we have a level and the 0.5 H for that level. So we'll be doing buckling checks on this strip, this portion of masonry, this portion of masonry, this portion of masonry. And then when we come across here, we've got a 5 meter height situation, and we've got the two strips here that load is being transferred onto, and we'll be doing buckling checks on those as well. In addition to the multi-level situation, then point loads that we previously only could apply to the topmost of the wall, as they are here, now have a Y value input so that they can be applied perhaps at an intermediate level or at any point within the wall, and they will perform their load takedown from that location based on the spread, the 60-degree spread, as I believe it is in the Eurocode. Okay, so one final bit of advice before handing back over to Andres is that I still would be an advocate that when your individual panels form simplistic load takedown, then I would still be an advocate of dealing with these in the software as two separate panels, because all you really, if you have some vertical load on the top of this panel, yes, it's going to transfer down to these panels, but really at this level it's nothing more than a UDL coming from above, and you can quite simply model this as one panel and then, or one design brief, and then model this as another design brief, so you still have your two separate panels. Why would you do that versus just doing it as one panel? Well, the main advantage for me is that currently our design output in terms of vertical load analysis samples whatever the worst condition is in all of this situation. So it might pick this 35 kilonewton per meter loaded strip of masonry and present the design output for this as being the worst case scenario for this overall arrangement. Whereas if you model the two panels separately, you do then get the design output for the vertical buckling check of the top panel as well as the worst part of the bottom panel. That would be the advantage for me. I guess that's a limitation of the current software in terms of how it's dealing with that and the output that it's presenting. But if you're telling us this is one piece of masonry, we're happy to just isolate the most critical part of that piece of masonry and present the output for you for that. So that's where we've got to. We're I think have had very positive feedback on MasterSeries 2025 since it's been released. One thing actually to note is this partially distributed UDL, which I didn't note. If you're still using the first August release of MasterSeries 2025, you might struggle to find where that is, and that's because it came a little bit later. I think it was around mid-September that we introduced the partially distributed loads, and you'll find those in the same place where you apply your wall top line loads. You now have an option to put in partially distributed loads in either the inner leaf or outer leaf, or whatever the case might be. So I will hand you back to Andres at this stage, and he's going to actually take you through a live presentation of the software to see all this in action.
Okay, thank you, Martin. Right, so before we jump into the new features, so let's start by looking back at how Masonry design was handled in earlier version of MasterSeries, and in fact how most other design software still approach Masonry wall design today. Some of you might remember our Masonry design webinar last year, where my colleague Patrick demonstrated how to model and design a complete building by splitting the walls into separate wall panels. Back then, the program didn't yet have the functionality to calculate a whole wall as a single unit, so we had to treat each section of wall as an individual panel. In that session, Patrick used this semi-detached house example with typical walls, each panel was designed separately with its own support conditions, loads, and openings. You might remember he talked through each wall panels on the front elevation, panels 1 to 4, defining the fixities along the edges, applying roof and floor loads manually, and then checking each panel individually for capacity. For example, here you can see panel 1 from the webinar, where Patrick assumed fixed supports on both sides due to the perpendicular party wall and internal return wall, fixed support on the bottom as floor joist on the first floor allow continuity, and the pinned top edge at the roof truss. Each wall segment had to be analyzed like this, one at a time, with separate loading and boundary assumptions. He then repeated the process for panel 2, 3, and 4, applying vertical loads from the panels above and lateral wind loads separately. The analysis was accurate for each individual panel, but as you can imagine, it was quite a manual process, and it didn't give you a full picture of how the wall behaves as a whole structure. This slide summarizes the main limitations of the traditional subpanel workflow. First, there is a repetition in modeling and design checks. Each wall panel has to be defined and analyzed individually, which takes time. Second, only rectangular panels can be analyzed, so more complex wall shapes couldn't be handled directly. Third, the process creates an artificial separation of a single wall into multiple parts, even though in reality it's a continuous structure. And finally, this method gives a less realistic representation of multi-story walls because the interaction between panels isn't captured. All of these points show why we needed a more integrated approach, which is exactly what MasterSeries 2025 now provides. So let's now switch from the slides and jump into MasterSeries Masonry Design to see how that works in practice, modeling and designing a gable wall using a new whole wall design workflow. So when we open the Masonry Design Module, it starts with a default simple rectangular wall configuration. Before we setting up the wall geometry, let's first take a quick look at the analysis settings. To design a non-rectangular wall, such as a gable wall, we need to make sure that the advanced yield line analysis option is turned on. The traditional panel method, which relies on the tabulated bending moment coefficients, can only handle strictly rectangular wall panels. The yield line analysis, on the other hand, can manage irregular shapes, openings, and multi-story walls, giving a much more realistic results. So now let's go to the wall setup to define the geometry. Here we can choose between a single leaf or a cavity wall, introduce piers, and this is new, define the wall as a gable wall. I will go ahead and turn off the option. Once that option is active, in addition to the standard width and height, we can now specify the gable geometry. Let's say our wall is 5.25 wide with a rectangular base height of 3.25 and the gable height of 2 meters. There are also two parameters to fine-tune the shape. The asymmetrical parameter shifts the apex horizontally, so we can model asymmetric gables. The hip flat parameter defines a flat section at the top of at the top for hip ends. I will leave both of these at 0 for now, so we have a simple symmetric gable wall. For the wall thickness, I will leave the inner leaf at 100 mil and the outer leaf at 102.5 mil. Next, let's move on to the supports, the restraint conditions, starting with the edge fixities. At the top, we will assume the roof truss provides lateral restraint, so this will be pinned. Both sides will be fixed as they are supported by return walls. And at the bottom, we have a DPC layer which affects the moment resistance, so we will assume a pin support there. Now we also have internal lateral supports, which can be horizontal or vertical. So this is one of the big new features in MasterSeries 2025. I will add a horizontal lateral support at 3.25 meter, representing the first floor level. By default, leaving the length set to 0 creates a full length support, but we can also define a partial length support. For example, if we had an open plan area where the floor only supports part of the wall. And that's it for setting up the wall geometry and restraints. Now let's move on to the materials. Under the material field, we will define both masonry unit and mortar. Starting with the inner leaf, masonry unit concrete blocks, group 2, execution class 2, category 2. For strengths, I will go with the standard 7.3 Newton per square millimeter block strength, which is a very typical value for structural concrete blocks used in load-bearing masonry. For outer leaf, the masonry unit is clay bricks, group 2, moisture absorption 7 to 12%, execution class 2 and category 2, and strength is going to be 15 Newton per square millimeter. Okay. For both leaves, I will set the mortar to M4, which is a standard medium strength mix suitable for typical cavity wall construction. Okay. So with that, our materials are complete. Now let's define the loadings. In MasterSeries, we can define both vertical and lateral loads, and even combine multiple load types on the same wall. Starting with the inner leaf, we will apply two vertical loads. First, a roof load, which is a concentric 0.5 kilonewton per meter top edge dead load. Then the floor load from the intermediate level. For the floor load, we will use the new partial line load function. one of the recently released features in the MasterSeries. This feature allows us to position a horizontal line load anywhere on the panel, not just at the top. In our case, we will apply 2 kilonewton per meter dead load and 1.5 kilonewton live load. The start point will be 0, and the end point will be the full width of the wall, which is 5.25. Since and the vertical position will be 3.25, matching the height of the floor and the location of the lateral support we defined earlier. And because this load is applied through the floor, we will add a 20 mil eccentricity to reflect that offset from the wall's centroid. For the outer leaf, we will only have the self weight, which is automatically calculated by the program, so there is no need to add any manual vertical load. We don't have a point load in this example, but let me quickly show you how this has also been improved in the MasterSeries 2025. Previously, a point load could only be added at the top edge of the wall. Now you can position point loads anywhere on the panel simply by specifying their horizontal and vertical coordinates. As before, you can define both dead and live load components, as well as bearing area and spadder or padstone dimensions for more accurate load transfer representation. Finally, let's add our lateral load. In this example, we will use a simple uniform area load of 0.85 kilonewton per square meter, representing the design with design wind pressure acting on the wall. And that's it. We have now set up the complete gable wall model. Since AutoSolve is turned on, I will need to click Analyze to run the calculation. AutoSolve is handy when making small adjustment, as it updates the result automatically. But when we're setting up a new wall from scratch, it can be a bit of disruptive. So I usually prefer to trigger the analysis manually once the model is ready. And that's done. On the graphics, we can now see the yield line patterns that the program used for the calculations, along with the lateral unity ratios. The green lines represent hugging moments, and the blue lines represent sagging moments. And as we can see, the program has automatically divided the wall into two analysis zones, generating independent yield line patterns for each zone. Here's zone 1 representing the ground floor section of the wall. That's the part below the intermediate lateral support, and zone 2 represents the gable section, which is the portion above the lateral support. If you're looking at the detailed calculation report, we can see separate yield line analysis results for each zones. Above the lateral checks, we have the detailed design results for both inner leaf and outer leaf, and below the graphics, we also have a summary of the overall design, including the maximum unity ratio from each design checks. And as we can see, our simple gable wall passes the design requirements. Now let's see how the situation changes when we add 2 openings to the wall. The first opening will be a window, position 1 meter from the left edge and 1 meter above the bottom, width 1 meter, height 1.375. By default, the program distributes the loads from the opening to all 4 edges, but we can also control how the load is transferred. For example, we can distribute it only to the top and bottom edges, or to the sides and top, or we can specify no load transfer at all, which is useful when modeling a true opening. The second opening will be a door, positioned 3.5 meters from the left edge and 0.275 meters above the bottom. Width is 1 meter and height 2.1. Once we have added both openings, we have to recalculate the panel. As we can see, the wall is now failing. It's about 17% overthrust overall, and if we zoom in, we can see what's happening. The top zone still works perfectly fine, with a unity ratio of only 0.26, but the bottom part of the panel, where we introduce the openings, is failing. Now, to strengthen the wall, we have a few different options. We could go back to the material settings and either increase the wall thickness or select a higher strength masonry unit, but another, often more practical approach is to apply bed joint reinforcement, which provides additional tensile capacity and helps redistribute stresses. We can add bed joint reinforcement to the inner leaf, the outer leaf, and or to both. In this example, I will start by reinforcing the inner leaf, as that's usually the more effective side for improving the overall wall capacity. There are 2 main ways we can define the reinforcement. First, we can manually enter traditional horizontal reinforcement. For example, let's add 2 3 mil bars spaced at 60 mil centers horizontally. The vertical spacing controls how frequently the reinforcement is placed up the height of the wall. In other words, which brickwork courses it applies to. Our masonry unit height is the standard 215 mil. So by setting the vertical spacing to 2 to 5 mil, we are applying the reinforcement to every brickwork course. Alternatively, we can select manufacturing reinforcement from the built-in library. For example, I will choose the Baker Murphy Compact I-50 and again apply it to every course by setting the vertical spacing to 5 mil. Of course, in addition to the bed joint reinforcement, we have also the option to add a wind post to the panel. Right, so let's go ahead and reanalyze the panel using this bed joint reinforcement we just added. And as we can see, the reinforcement has had a significant effect. The wall that was previously overstressed by around 70% now works. The unity ratio for zone 1, which is the ground floor section, has reduced to 0.941, and for zone 2, the cable section above, it's only 0.218. So that was the process of how we can design a gable wall in MasterSeries 2025, handling any combination of openings and applying bed joint reinforcement as needed. As we can see, the software allows us to model non-standard complex wall as a single unit, automatically divide them into analysis zones, and carry out the realistic yield line analysis. This gives us a clear and straightforward indication of which part of the wall is failing and how we can effectively strengthen it. In the next part of the demonstration, So in the next part of the demonstration, I would like to quickly review a few additional wall shapes and structural types that can now be handled in MasterSeries. First, let's look at a multi-story wall. In this example, we have both a ground floor and a first floor with horizontal lateral support provided by the intermediate floor level and the vertical support, representing the effect of an internal return wall. The program automatically divided the wall into 4 analysis zones and performed independent yield line analysis for each one, providing a realistic representation of the wall's true behavior. However, as Martin pointed out, if your multi-story wall is simple, strictly rectangular without complex loads or complex geometry, it's perfectly fine to stick to the traditional sub-panel method. Next, we have an asymmetric gable wall. Here, the apex is offset horizontally from the center with 1 meter. This allows us to model walls that are not perfectly symmetrical, which is common in extension or in irregular buildings. Again, the floor joist provides the lateral restraint for this wall. The third example is a hipped wall, which features a horizontal flat top at the apex. This form is particularly useful for certain roof geometries, and with MasterSeries we can easily handle these complex wall shapes and perform an automatic yield line analysis. And because many of you are new to MasterSeries, I would also like to quickly show 2 additional structural types that can be designed using the Masonry module. Freestanding wall. This is the first example. So freestanding wall, so this is fixed at the base, but free at the top and sides, subjected to lateral wind loading. To ensure lateral stability, in this case, we added piers along the wall to provide the necessary stiffness and resistance. And finally, we can also design masonry columns. In this example, the column is fixed at both ends and carries an eccentric combined dead and live load at the top. So these examples demonstrate just how flexible the MasterSeries Masonry Design Module has become, covering everything from simple rectangular walls to complex multi-story or irregular geometries, all within a single intuitive workflow. Okay, so that brings us to the end of the demonstration. So, ladies and gentlemen, I would like to thank everyone for attending today. I hope you enjoyed the session and found the new Masonry design features in MasterSeries 2025 as exciting and inspiring as we do. We look forward to seeing you at our next webinar. If you have any questions, please feel free to get in touch with us through our usual channels. And if you would like to try out the software, just visit the MasterSeries website and fill in a trial request form. After the webinar, please do not forget to take a moment to complete the short 1-minute survey. It really helps us understand what you enjoyed and how we can make future sessions even better. So once again, thank you very much for joining us today and have a great day.